Hello everyone. Today I wanted to show you some meteorites that I'm generating for my game, and you can see them on the screen right now. I'm pretty proud of them, and I think for what they are, they look very good. So if you want to try generate your own asteroids, I would link you to my GitLab account where you can find all of the code. However, if you are curious in how I made them, then I would like to show you right now. Now, if you're only interested in the code, you can find it right here. So we are hard coding an icosahedron, and we are doing that with these values. In addition to the vertex position, we're also generating a color, a normal, and a UV. And then later on, we are subdividing each phase a number of times. And we can subdivide it as many times as we want. Now, for each time you're subdividing, obviously you're adding more faces, you're adding more memory, and you are essentially making it harder for the GPU to render it. At the level that we're doing it, it doesn't really matter that much. We subdivide it 3-4 times. But if you're subdividing it, 7 or 8, you're suddenly dealing with hundreds of megabytes of data. Now, right here is the magic values that I got from Unity, actually. Now, in this case, we are only generating the vertices that we actually need. So if you have ever unwrapped a sphere before, or any 3D model in, let's say Blender or Maya, then you know that you basically have to duplicate the vertices in order to properly unwrap it into small islands of vertices. Now, the reason for duplicating the vertices is you cannot unwrap a closed object perfectly on a UV map without having some kind of overlap. Now, the cool thing about it is that you're taking the normal vector of the vertex in order to generate the UV map. So we can subdivide it as many times as we want, and we don't really have to think about where we are placing the vectors. So again, if you want it to be perfectly unwrapped, you need to duplicate vertices. That's not what we're doing here, but I think that you will see that it still looks pretty darn good. Now, there are a couple of ways of generating an icosahedron, and the way that I did it is the same as the one on Wikipedia, which is basically we are taking 3 rectangles, and then we are placing them perpendicular to each other, and then we are connecting all of the edges as triangles. And if you do that, you basically end up with the icosahedron. Now, of course, we want the icosahedron to be regular. We want every side to be the same so that there's no distortion or scaling going on. Now, the way we do that is by using what some people call a golden rectangle. And a golden rectangle is just a square, perfect square, with an added side b, such that a over b is equal to phi. And phi is, of course, the golden ratio. So here you can see a graph similar to Wikipedia, where I have drawn an icosahedron, and I put in the perpendicular rectangles. And you can see here that we have a plus b, and a are the sides, and all of the edges of the rectangles correspond to the vertices. Now, perhaps you remember Pythagoras from school. So you have a2 plus b2 equals c2. Well, we can do the same thing in 3D, where we take a2 plus b2 plus c2, take the root of that, and then we get the length of the vector that is to each vertex. Now, because all of these rectangles are the same size, and they are also perpendicular to each other, they all happen to have the same length. And this length, if we are given if we are taking b equals 1, then we automatically get a equals phi because of this relationship over here. And then we can calculate the length is equal to 1, which is 1 squared, plus the golden ratio squared. But then we want to normalize it, because all of these vertices, we want them to be at an equidistant length of 1 from the origin. So we take b, which was 1, and we divide it by the length. And then same thing for a, which was phi, divided by the length. And then all of our vertices in the icosahedron, they're just all of the permutations of 0, b, and a. So that gives us the icosahedron right here. And as you might be able to tell, it's all regular triangles equidistant from the center. So how do we subdivide this to make it rounder, for example? So here's one of the triangles, for example, and I have just labeled the vertices A, B, and C. This is one face of the triangles that we are rendering. So what we are doing is we are calculating new vertices that are right in the middle of each side of this triangle. So in vector math, this is pretty simple to do. All we really need to do is we take the vector b minus the vector a, so we get the difference between them. Then we take half of that because we want the middle, and then we add a to that vector. So we start at the position a, and we go halfway the vector b minus a. And that gives us a new point, which I call a and b. We do that 3 times for all of the different sides. So with these new points, we can generate new faces. And it's pretty simple actually, because all we need to do is we take A, AB, and CA, that's one new face. Take B, BC, and AB for another one. C, CA, BC, that's a third one. And then finally, we take the middle one, which is AB, BC, and CA. So what we have done is we have doubled the amount of vertices, and then we have quadrupled the amount of faces. And this is also why very quickly you subdivide a couple of times, and then your faces and everything goes up to tens of thousands very quickly. Now there is still one issue with the vertex that we have generated, which is clear here. We have taken the middle point between A and B, but as you can see, that is not on the circle. Now, the good thing about a circle is that all of the points are the same radius away from the center. So all we really need to do is we need to take the AB vertex and we normalize it to be the same length as A and B. So this is how it looks like when it's subdivided once. So it's hard to tell, but we have multiplied the number of faces by 4 and also spherized it. So it looks a lot more rounder right now. And for completeness sake, here is when we subdivide it 5 times. So here we have 10,000 vertices, and you can see it's pretty darn smooth. Now there is still one issue, and if we go a little bit closer here, maybe we can see it better. There's this line where the UVs are kind of messed up, and we can see it goes right from the North Pole. So it's pretty good all around, right until here. Then you get like this zigzag pattern all the way down, then straight, zigzag again to the South Pole. And it kind of looks a little bit off. Now, these UVs are actually the entire UVs around from here all the way around this texture. That's all smushed together in here backwards. And you will see the reason why. So here I have opened our model that we generated in RenderDoc so we can inspect it more closely. So we can go to the draw and we can see our globe here. It's perfectly sphered. And we are having also all the triangles. We can inspect them in detail. Now, if you haven't done this before yourself, then here's a personal tip. You can actually right click here and select the UVs as position. And then you will get, if you look at the vertex out, then you get your UV map. And what you might be able to see here. So we are having a bunch of small triangles, which are the properly mapped UVs. But then you have these lines across. And these are the lines that, you know, without duplicating the vertices, you can't really avoid them. And the higher you go, the thinner the scar is. Now, of course, we are having a very nice moon-looking kind of asteroid, but we want to generate something that looks more like a meteorite. So how do we do that? Well, it's pretty easy to just apply a little bit of vector math again. So we take a random value. So this goes between 0 and 1. And what I decided to do was I decided to divide it by 2. And remember that A here is a magnitude of 1. So we're adding 0 to 0.5. And then we're multiplying it by 0.5. So this is just like extending it a little bit depending on the random value. And then later when we are subdividing it, instead of going just up, I'm also going a little bit on the side. Now it's pretty important that you are, when you're moving to the side, that you're going a very small distance. And the reason for that is otherwise you get vertices going across to some other vertex. And then you have the issue where the triangles might intersect. And that looks pretty bad. Now what I decided to do was I decided to multiply it default by a value of 0.1. However, 0.1 times 1 gets pretty high pretty quickly, depending on how many subdivisions you have, because like each triangle becomes smaller and smaller. So what I decided to do is to take the root of the number of faces that I multiply with, and I add that to this 0.1 factor. So the result of all that is that we get a meteorite that looks something like this, and it's all generated based on one seed value. So essentially I can generate a U64 amount of meteorites, and I can even generate the exact same one if I just store this value. So I don't have to store the mesh or anything. Every time I want to display it, I can just regenerate it in like a millisecond. So that's all I had to say about meteorites for now. If you would like to follow the development of this game, then you can follow me on Timps Live, where I live stream, also on Twitch/Timps. And if you would like to take a look at the source code, you can go to my GitLab, or you can visit my website, timps.tv, and you will find all of the links there. And my goal is to soon have a playable version on my website for you to enjoy. So thank you very much for watching.